To do calculations with the mirror, there's two main equations you need to know. You need to know that the center of curvature is twice your focal length. So if you're given your focal length, then you double it to get your center of curvature. The other thing you need to know is that 1 over your focal point, and let's make those focal points so that we don't get them confused with frequency, is 1 over di, which is your distance to your image, plus 1 over do. And then to get our magnification, that's negative di over do, or it's hi over ho. And sometimes what we'll do is we'll set this part of the equation equal to each other. So you might be finding the magnification, or you might be using the equivalences in the magnification equation to find the height of the image or the height of the object. Okay, in order to have the math work out, we need to have some sign conventions. So basically, anything that's not really there is going to be negative. So if it's not real, it's going to be negative. If it's real, it's going to be positive. So what's that mean? That means our focal point. Our focal point for a concave mirror. A concave mirror has the focal point outside the mirror, because here's our concave mirror and our focal point's here, and the light's coming in this way. So the light will come in and it'll bounce off this and bounce through our focal point, and so the focal point is really on that side. So focal point for a concave mirror is positive. For a convex mirror, your light comes in this way and bounces off this way, and so it appears to focus back here. It's not really focusing. So convex mirrors have a negative focal point. Now, distances, your di, your object distance, do, is pretty much always positive. Your image distance, if it's real, it's going to be positive, because remember, a real image is formed when the light rays really cross, and you have real light rays. If it's virtual, so if you have a virtual image, you're going to end up with a negative di. So that's one of the ways you can tell if it's real or virtual, if you end up with a positive di or a negative di. So applying it to a problem, where will the image of a 2-meter tall truck placed 10 meters in front of a concave mirror with a focal length of 0.5 meters be located? Okay, so the focal length of our mirror is 0.5 meters. So we have 1 over our focal point is equal to 1 over di plus 1 over do. We're looking for di. So our focal point, 1 over 0.5, is equal to, we're looking for di, so we're going to leave that, plus, okay, so which one? 2 meters or 10 meters is our do. Okay, since the truck is placed 10 meters in front of the mirror, that's the distance to our object. This is the height of the object. So we're going to use 1 over 10 as our do. So you want to use on your calculator, you want to use that x to the minus 1 button. So this is going to be 0.5 to the minus 1, and then we're going to subtract the 1/10 because we need to move that over here. So that's going to be minus 10 to the minus 1, and that's going to equal 1 over di. So we end up with 1 over di equals, so 1 over di equals 1.9. So we need di, so we have to flip that over. And so when we flip that over, that is going to give us di equals 0.53 meters. Okay, so this is where we'll find our image. If we put a screen at 0.53 meters in front of, or 53 centimeters in front of our mirror, we should actually be able to see our car in the mirror, or actually on the screen. So, is this image real or virtual? Okay, we know that it is real because it's positive. Since this is a positive 0.53 meters, this is a real image. Now then the question, magnified or reduced, that's a little bit trickier. Or to find out if it's magnified or reduced, we're going to use the magnification equation. So the magnification equation says that the magnification is negative di over do. Okay, so our di is 0.53, and our do was the 10 meters in front of 10 meters, so that's going to give us a magnification of 0.053. So that, since this is less than 1, that means that it's smaller, it's reduced. Since it's less than 1, it's reduced. And then the negative, or the orientation, okay, remember this is a real image, so the orientation is inverted since it's a real image. Real images are always inverted. We can also tell that because our magnification is going to end up being negative also, and so when we do our HI over HO, okay, our height of our image, we don't know what it is. Our height of our object is 2 meters, and that's going to equal a negative 0.053. And so when we solve for HI, we get a negative 0.106 meters. And so what that tells us, the negative there tells us it's inverted. Okay, same idea, same question, except for now our car is in front of a convex mirror. So the difference is, the only difference is we're using the same equation. One of our focal point is 1 over di plus 1 over do, same equation, but since it's a convex mirror, remember a convex mirror has a negative focal length, so we're going to make this a negative 0.5 is equal to 1 over di plus 1 over 10. And so solving for di, we get 1 over di is negative 2.1, and so di, when we flip that over, is 0.48 meters. Negative 0.48 meters, because we have the negative there. And so this tells us that it's a virtual image. Okay, since our di is closer than our do, since the image is closer to the mirror than the object, it's going to be reduced. Okay, we can actually find out how tall that is. Remember I said at the beginning we could use the di over do is equal to hi over ho to find out the actual height. We know that it's a negative of a negative 0.48 over 10 is equal to, we don't know hi, that's what we're looking for, over the 2 meters that it originally was. So solving for hi, we get, cross multiply, divide, we get 0.096 meters. So that is much smaller than the original 2 meters of the car, so it does get reduced. And since it's virtual, it will be an upright image. We also know that because our HI is positive, so it's upright. And that would be everything. So these are the same basic ideas that we're going to be applying to all of our mirror calculations.